Welcome back to General Structures 2 and Lateral Forces, Lesson 4, and this is the earthquake design example, and we're starting on page 114, and this, as I would say, is part 2, I believe. Alright, and we're going to go ahead and start where we left off. We had 542 pounds per linear foot, and this, once again, is 183. That's 183 coming from 183 pounds per linear foot coming from this wall right here. Whoops, wrong. Let me switch it up on colors. Make sure I have the right thing. Yeah, looks good. 183 on this wall coming from there. 183 on this wall coming from there. And then there is, 176 coming from the diaphragm, the roof diaphragm itself. And we add all those together, and you can look at this like a beam. Let's look at this as a beam. Let's say we have a beam. Well, let's just make it a line, or like so. That's a simple beam, and we're looking at it in this plane right there. So let's call this, let's call this what? X, Y, and Z. So we're looking at this in the XY plane, and you can look at it as a simple beam. Let's put a reaction or a support right there and a support right here. So let's kind of flip it, and we can look at it as a simple beam with a uniform loading on it that is 542 pounds per linear foot. So I hope that makes sense. We're looking at it like this. This yellow, I mean this light blue, is the, and I flipped it to make it look like that. That light blue is at 542. It's this pink plus the yellow plus the pink. I hope that makes sense what I'm trying to say right there. So we look at that diaphragm as a simple beam, and if we do that, you can get a few different you can get these reactions, and that reactions is along this entire, so it's a real, you can just think of it as a really thick beam, a 60-foot tall beam. And actually the reaction would be down here at the roof, but for better or worse, there, that's what I'm talking about. And we can just go ahead and say it's up there, even though it would actually be at the roof, because that's what we're talking about. And it's 60 foot deep. So we need to figure out what is that reaction right here, and then we're going to say, okay, and it's also spread across that entire 60 foot. So let's figure out what the reaction is, the reaction for this, and we can use a simple type of equation since it's a uniform distributed dead load, or you could go ahead and do it the old school way, which, heck, I'm going to do it that. Just to help out on your moment diagrams and whatnot, and your free body diagrams. Let's just say free body diagram. We go like this, and I'm going to get on my calculator, but we know that this is your equivalent load for this uniform distributed dead load. Well, that's not a dead load, it's called an earthquake load. It's a percentage of your dead load. That's how they look at earthquake loads. But you get 542 pounds per linear foot times, what was this, 150 foot, I believe. Let me look back. Yes, this is 150 foot right here. Whoa, that went way off screen. Okay, my pad's a little bit off here. There, it has been fixed. Alright, so this is 150 foot right here. So this L equals 150 foot. So 542 times 150 foot, you get an equivalent load of 81,300 pounds, or 81.3 kips. And if you know what you know, you said, well, hey, I know that this is divided by 2, since it's equivalent. There's an equivalent load going to each. But since you may not know that, you could sum the moments about this point right here. Let's call it point A. This is point B. Let's go ahead and do it up here. In the sum of the moments about point A, we're going to say that this is positive. Once again, this is review. You could easily just do what it would be WL over 2. But this is just figuring out where that WL over 2 comes from. And you can go back into some older videos, and I've gone over where WL over 2 comes from, and then you have your moment equals WL squared over 8. That's your maximum moment at L over 2. And I hope I'm not speaking gibberish right there. That was a little bit of engineer talk right there, skipping over the simple explanation. Alright, anyways, let's go ahead and continue on here. We know that A times 0 is 0. We have it's a positive 81.3. I'm going to change this to kips just because I don't like writing out all those zeros. And then that's going to be 150 divided by 2 is 75 foot. And then we have, that's going to be a negative B times 150 foot. Alright, when we come out to get this, we're going to have a positive 81.3 times 75, and then it's going to be negative B150. So if we add B150 to each side, 150B, you just have to take 81.3 times 75 divided by 150. And hopefully that makes sense to you, that process. And if not, then go back to some of the older videos, and those can help. So 81.3 times 75 divided by 150 is 40.65. So B equals 40.65, or, and that's going to be kips, and that always equals 4,650 pounds, which should equal WL over 2, which should equal what? Remember, W is 542 PLF times 150 feet divided by 2. Alright, and using the calculator, 542 times 150 divided by 2 equals 4,650. Equals this exact same number. So that's how you get WL squared over, or WL over 2. It's the same as going ahead and doing that. And then I guess since you got this right here, you have the reaction at B is 4,650 pounds. You could do the sum of the forces in the y direction equals 0. You could say, okay, I have a positive A, since we assumed it's up. I have a negative 81,300 pounds, and I have a positive 4,650 pounds. And you will find out you put A on this side, and you end up adding 81,300 or negative 81,300 and 4,650, and you get a negative 4,650. You put it on this side, it becomes positive. A equals 4,650, and you will also see that it works out that way. Alright, that was probably a lot of unneeded issues, but we got the reaction. In the end, we have our reaction. So we have our reactions right here. It's going to be going in one or the direction or the other. Depends on the period, which way that's going. But we're going to go ahead and erase all that information. And in the same way, you could get, and I'm not going to do it just because that took up a lot of time, but you could go ahead and figure out using, once you have your free body diagram, you get your shear and your moment diagrams. And our reaction equals 4,650, I believe. Let me look at my calculator. I still have it. No, I don't. But 4,650 was it, because I just remember. And that's going to be in pounds. And now remember how I said, since it's coming down like that, but it's divided along that entire length of that 60-foot wall. So we want to take 4,650 pounds and divide it by that 60 foot. And we're going to get, this is, you select the plywood diaphragm from the UBC table 23-I-J-1, and that's it's put on page 98, which I need to go find. But let's figure out what this is. 4,650 divided by 60 equals 66 or 67 777.5, and that's pounds per linear foot. Then you take this number and you go in. This is our minimum we need. This is what it's seeing, so therefore we need a capacity that's greater than this. So let's go to that table I just mentioned on page 98 in the study guide. And once again, this is the UBC. It's reproduced from the UBC table 23-I-J-1, allowable shear in pounds per foot for horizontal wood structures, panel diaphragms with framing or Douglas fir, larch, or southern pine. That's a long title. Anyways, we go down, so we're looking for anything greater than 677 or 678, let's say. So we go down, let's look at a common nail size, minimum nominal panel thickness. That's not nearly large enough, so we go to 5/16, 3/8. Let's go all the way up to 15/32. So we go over 640, and then it has 730, and 730 is large enough, but 640 is not. And if we go down, 600 is 3/8. And so it looks like what we're going to need to use is a 15/32 thickness, and that's panel grade structural 1. And it looks like it has common nail size is 10D. And it has the nail spacing up on. If you go straight up, you can see it says nail spacing inches at diaphragm boundaries, all cases at continuous panel edges parallel to load, and at all panel edges. And it says that spacing is 2 inches, and then it says nail spacing at other panel edges is 3 inches. So I'll just put 2 inches or 3 inches. Just to simplify it here. So let's go back to the beginning and see what they were asking for. It says determine the diaphragm shear, which we have done. This is diaphragm shear. And it says select a plywood diaphragm, and that's what we did right there. We had to use that thickness at that nail size at that spacing. And then it also says that we need to calculate the maximum chord force in the diaphragm. And if you think about it, that would be, and I'm not going to do the moment diagram because once again that wasted a lot of time. Well, I won't say wasted, it would take a while just because that's how moment diagrams are. But anyways, what it is you have that beam. Let's do it right here. This is the chord. So for instance, if it's going, I actually drew it incorrectly. If you're looking at this diaphragm like a beam, here's your beam once again, and it's a thick beam, so it's actually that thick a beam. It's a tall, high beam, or that's not called high, but tall beam. So if it's the forces are going this way, you have a uniform distributed load going this way, then if you think about it, this will be in tension. Actually, I did draw it correctly. And this will be in compression. Let's draw like that. So compression, tension. So you can just think about it. Any wide flange beam is probably the best way to think about it. Tension is going to be your bottom, and compression will be your top, because it's going to be trying to smile like that. So compression, tension. And that should make sense. If it doesn't, go look at some older videos, and I hopefully explain that well, or I will have some more videos in the future that will explain that even better. And hopefully some website text and whatnot. Anyways, the way you figure out that max tension chord force is WL squared over 8, which if you recognize, this is your moment. So you want to figure out what your moment is, and then you want to divide it by your depth. And it's similar to how you look at a truss. So you look at it as, hey, these are a chord of a truss, and therefore I want to figure out what the moment is. I want to divide by the moment arm, and I will get the forces. And I have run out of time, so I will start this on the next video.